Hi, I'm Grace. I graduated from Richardson in 2011, and I'm here to talk to y'all today about the wonders of differentiability. What is differentiability? Well, a function is said to be differentiable if at x equals c, the derivative of f exists at x equals c. Which is just a fancy way of saying that we can figure out the slope of an equation at a point if that point is within a differentiable function. Yeah? That'll make more sense as we go through it, but first, let's focus on local linearity, because that is what all of this is contingent on. So, let's say I have a calculator, and on that calculator we have a circle. And on that circle we have a curve. Let's zoom in on this circle. On this curve on this circle. Do you see what I'm doing there? Just moving on up there and zooming in. That looks rather curvy. Okay, but what if we zoom in again? Can you see that? Camera, work with me here. Oh, okay. Looks a lot straighter. Let's do it one more time. And that looks real straight. That looks linear, right? We could keep going and going and going, and the line would just become straighter and straighter. So this just means, and you could do this at any point on the circle. You could zoom in at any point, and this would still work. And this means that each point on a curve is locally linear. You could make a sphere out of straight lines, is what that's saying. And if you still don't believe me, let's try drawing something. Okay, you see this lovely lady? Alright, I'm going to draw a straight line here, and 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 another straight line. Do you see that curve starting to form? All these straight lines? If you were to take a pen, you can draw the curve that's starting. See that? Ain't that pretty? So basically what we did is we first drew all the tangent lines. And then we formed the curve out of that. And usually what you see is you'll have a graph, and somebody will draw a curve, and then you will then have to go in, and draw the tangent lines. Yeah? We just went the other way around. So okay, let's say you have this parabola. You can draw tangent lines at the different points along this parabola. So let's say here, you can draw a tangent line. Here you can draw a tangent line. Here you can draw a tangent line. And all of these have pretty clearly defined slopes, right? It's pretty clear to see that if you were to take the locally linear part of the graph here and extend it to become a line, you would get this straight line with its own slope. Yeah? That's a derivative. The slope at a point, the rate of change at a point, is the derivative. So when we reach 2, which is the bottom of this curve, and it's at, intersects with the x-axis, the line's horizontal. Well, what's the slope? Well, I'm sure y'all have all heard of the fabulous Hoy-Vux rule. And we're going to deal with this later, so I'm just going to box this off. But right now we're going to focus on Hoy. Hoy stands for horizontal 0 equals y. Okay, so what this is saying is that when you have a horizontal line, the equation is y equals 0. Okay? And as we all know, y equals, can you still see that? Y equals mx plus b. with n being the slope. If that equals 0, then that means you have 0x plus 0, and the slope is 0. Yep. Cool. So then we know that the derivative at 2 is 0. Yeah? F prime of 2 equals 0. Okay? Well, what if you have an absolute value? So this is the same thing. Well, you know, it's a different graph, obviously. This is f of x equals the absolute value of x minus 2. It's the same thing as far as drawing tangent lines, in that this is straightforward, and this is even more so. And that when you draw the tangent lines, they are going to be the same slope as this arm of the V. Yeah? It's going to follow this exactly. But what happens when you reach the intersection? Dun dun dun. You have this line with this slope, and then you have this line with this slope. You have two competing slopes. No! What do we do? Well, this is called a teetering tangent line. Teetering tangent line, and that is an important term. Because you can think about it like if you put your pen here, it's teetering. It's like a teeter-totter. You know, it can go either way. Okay? So there is no derivative here. There's nothing, you can't find the derivative. Because you have a teetering tangent line, and there is a sharp, ooh, that is a P, sharp turn. When you have a sharp turn, you're going to have a teetering tangent line. What we would prefer when doing derivatives, if you actually want to find a derivative, is a curve. Because at a curve, whether you're approaching it from the right or the left, these two sides are approaching it with the same slope. Yeah? Here, these two sides are approaching it with totally different slopes. Okay, so you'll see this again. We'll see this again in a little bit, but this is the way that you can picture this, yeah? This is what we would call a cusp. And it looks like a great winged beast. You know, flying off into the distance. But this is the exact same thing as, you know, what we were saying before with the absolute value. It just has curved wings. Curved little arms here. So if we were to take this and we were to zoom in on it, so let's pretend to zoom in here, you would see this. You would see a sharp turn. Yeah? Sharp turn returns. So what do you do here? You have, again, two completely different slopes intersecting at this one point. So there is no one clearly defined derivative. There's no one clearly defined slope here. So there is no derivative. Okay? Because remember, you have the teetering tangent line. Okay? Alrighty. Let's look at the next example. You have f of x equals x minus 1 to the 1/3. And what this gives you, and this is kind of a wonky graph, but what you're going to get is you're going to get this kind of a graph with it turns vertical here. That's what this line means. It's supposed to be vertical here. Okay? Remember when we were talking about Hooy-Vux earlier? Good times. Well, now we're going to talk about the Vux part. Vux is vertical, undefined, equals x. Okay? So this is saying if you have an undefined, if you have a vertical line that is going to have an undefined slope. So right here, though these are coming towards it, like when you reach x equals 1, and you get your vertical line, these are both approaching with the same slope. You have a curve. So that's not the problem here. The problem is that when they do reach it, it's in a vertical slope. And if x equals undefined slope, then you have no derivative. So if you wanted to find the derivative at x equals 2, you would have to find a point at which these, where you have two lines coming together to intersect, right? Because you want the same slope on either side, whether it's approaching from the right or whether it's approaching from the left. Well, sadly, the most, tragic love story, these lines never touch because there's an asymptote. So there is nothing, there is no slope to find. There is no local linearity. There's nothing we can zoom in on to have a straight line to find the slope from. We just talked about all kinds of different ways that you can picture, that you can explain how you find derivatives at different places. We need to show this more mathematically, though. Why is this all true? What formula shows us that this works? F prime of c equals the limit as x approaches c, f of x minus f of c over x minus c. Notice that this is the formula you learned in pre-calculus for the slope of the tangent line, which makes sense because this formula is the derivative formula. This is how you find the derivative. This is how you find the slope at a place. And we just talked about how when you find the slope at a point, you're finding the slope of the tangent line. You're finding the slope of the, of this. Of it, that just ties it all together right there. That's just lovely. That's art. We are told that f of x equals the absolute value of 2x minus 6. And we are told that we want to find the derivative when c equals 3. So I'm going to take a calculator. I'm going to show you this because picturing is always better for me for learning. We can see that it's a sharp turn at 3. So at 3 is when this intersects, and we can tell that the sharp turn, and we already know that we can't find the derivative there. Derivative does not exist, but we have to show that using the formula. Okay? So, let's see what our formula is again. Write this in green. We have f prime of c equals the limit as x approaches c of f of x minus f of c over x minus c, right? Okay, so let's see what we can plug in here. We're already told f of x, we're already told what c is. What is f of c? F of c equals absolute value of 2 times 3 minus 6, and that equals absolute value of 0, which is, of course, 0. Okay? So what is our equation? Our resulting equation. The f prime of c is the limit as x approaches 3, because we know that c is 3. We could actually probably plug in 3 here too, but alas, it is too late for me. So this is the absolute value of 2x minus 6 minus 0 over x minus 3. Yeah? Cool. So, let's pretend that we didn't know that there was going to be a sharp turn there. And we didn't think about it too hard beforehand, so we're like, okay, let's just plug in. We're told that we want to find the derivative at x equals 3. And we're like, okay, let's just see. So if we're going to plug it in, limit as x approaches 3, 6 minus 6 minus 0 over 3 minus 3. This is 0 over 0. And we're just panicking. We're like, oh my god, what? Well, I would recommend that we graph. I would recommend if you run into this and you're just freaking out because you've got 0 over 0, if you're on a test or something, to graph it, see if you can figure out what's up. But another way you can go about it, because that, you know, that can help you out to figure out what you need to do next. But for this situation, we want to see what's happening on either side of this equation, because there are multiple things that could be going on. It could be a sharp turn, it could be a vertical line. I mean, we don't know, right? Let's pretend we don't know what an absolute value looks like. So we're going to see what is happening on either side of that point. We want to know what the curve is leading to, okay? Or if there even is a curve. So we want to find f prime of c when x equals 2.9 and when x equals 3.1. Okay, so these are just, you know, this is just around 3. Just numbers around 3. Yeah, and they're close to 3. And they're going to be easy for us to figure out, which is why I chose them. They're kind of arbitrary, but not really. So we're going to plug it in. We're going to plug these in back to this equation. So we want to know the f prime of 2.9 equals absolute value of 2 times 2.9. Let me make sure this is big. 2.9 minus 6 over 2.9 minus 3. Yeah? Equals negative 0.2 absolute value over negative 0.1. And this is just something I did beforehand on the calculator, but I mean, it's just pretty straightforward. You can see that that is going to be negative 0.2. This is just that. Equals negative 2. And this is pretty straightforward. It's going to turn into a positive. This is going to be a negative on the bottom. This is a negative. Yeah, we're all smart. We're all good? Okay, so this is negative 2. So coming from the left to 3, you know, coming from the, so like if we have this graph and we have here, coming from this side, the slope is negative 2. But what about coming from the right? What is the slope? So we have the f prime of 3.1 equals, can you see this still? Move this up. 3.1 is times 3.1 minus 6 over 3.1 minus 3. Yeah? So just to reiterate, I'm just plugging 3.1, the c, into this equation. Yeah? See that? Pretty straightforward. And then this is the absolute value of 0.2, but this is a positive 0.2 this time over 0.1. Both of these are positive. It's going to be a positive number, and this is going to be a positive 2. Okay, so let's pretend you didn't know this graph. Let's pretend you didn't know this was an absolute value, or you didn't recognize what this graph was going to look like. But you don't need to know that necessarily. Once you do all this work, you can see that, oh, these are two drastically different slopes. This is probably a sharp turn. There is no derivative here. Okay? So no derivative where c equals 3 because there is a sharp turn. Sorry, I know you can't see over my hand, but yeah. Solid. All right. B. F of x equals x minus 2 to the 2/3 c equals 2. Alright, that's what we're told. Same exact directions. We're supposed to show, using our handy-dandy formula, what is happening at c equals 2. Okay? So, let's plug in the formula again. I'm going to use a different color because I want to, and I can. And this is still focused? Yes? Okay. So, f prime of c equals the limit as x approaches c of f of x minus f of c over x minus c. And if you do write this down a new time, each time you're doing a homework problem, if you write this down new every time, it will help you remember. So that's a handy dandy little life hack there. So let's plug it in. Let's plug in everything we know up here into this. Oh, but first, so we know what f of x is. We know what c is. We want to know what f of c is. So I'm going to use a different color again. Back to the same purple. So f prime. No, I'm sorry. No, we're not doing that yet. F of c, so f of 2 equals 2 minus 2 to the 2/3. You see that? That is just 0 to the 2/3, which is 0. So once again, we don't have anything to plug in for this, so we're just going to write this all nice and pretty as f prime of c equals the limit as x approaches 2 of x minus 2 to the 2/3 over x minus 2. Right? That's that. Now, once again, this isn't, we don't even know what this looks like. We don't know what this looks like. And I'm not going to show you. I'm not going to show you right now. So we are going to, if we are asked to tell us, okay, so if x equals c equals 2, and we want to know what the derivative is there, we're going to plug in 2, so limit as x approaches 2 of 2 minus 2 2/3 over 2 minus 2. You see that? We get f prime of 2. So I just plugged in 2 for each of these x values here. You get 0 over 0. And once again, we're just distraught because we have appeared to failed. But alas, the graph has failed us. Stupid function not being differentiable at all points. So, once again, we're going to try and see what is happening leading up to this point. What is this graph even doing, approaching from the left and approaching from the right? So let's see. So let's pick two points. I'm going to find the slope at 2.1 and 1.9. Okay? And that way we can try to get an idea of what this graph even looks like and what might be going on. So I'm going to switch to green, because this is a new step in our process. So okay, once again we're going to take this and we're going to plug in f prime of, let's start with 1.9 because you know this is from the left. This is how it's approaching from the left. So let's take a Western view to this. And the limit as, oh, we don't have to write limit anymore. But if we have 1.9 minus 2 to the 2/3 over 1.9 minus 2. Alright, so all I did here was I took this equation, plugged in 1.9 for x, and you get 0.215 blah 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 blah, it's a long number, over negative 0.1. That is the same thing as negative 2.154 blah 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 blah. Okay? Make sense? Yeah? I wish I was talking to actual people who could answer that question. The flip curriculum's awesome! And I really do strongly believe that. So, anyway, that's, I digress. So, from the right, when we're approaching it, we're going to see what's happening over here with 2.1. So I'm going to plug 2.1 into this equation. So 2.1 minus 2 to the 2/3 over 2.1 minus 2. That equals 0.215 dot 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 over 0.1. And this number, though I'm not going to show you the real long number on the calculator, this number is the same as this number. Well, up to like how many digits I was shown, which was like 10. So this equals positive 2.14 dot 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 dot. And you can see now these are two drastically different slopes. So once again, there is no derivative when x equals 2 because, oh, can you see this? Because there is a sharp turn. Okay? So I'm going to show this to you really fast. It's that winged creature again. And just as a reminder, because these two are A and B are very similar, and they're both sharp turns, when you, zoom in on this point, when you zoom in at this point, when you zoom in at 2, you're going to see something that looks like an absolute function. And that is like the two lines that are on either side of the point are both going to be locally linear. Okay? Get pumped. F of x equals x squared plus 2, x is less than 1, and 3x when x is less than or greater than 1. So I haven't shown you an example of this before. But this is what we've been given. We want to know when c equals 1. What's up? So I'm going to grab my purple, and I'm going to just sort of sketch what I think might be happening here. We know this is a parabola, so it's going to probably look something like this. And then we know this is a straight line, so it's probably going to look like a straight line. But do they intersect? That's the first thing you want to try and figure out. Do they intersect? Because if they don't intersect, there's no continuity. You can't, find there's no point, there's no approaching on either side. You probably have a teetering tangent line going on. So, at c equals 1, well, you don't even have to plug in that. At 1, do these intersect? Well, we have 1 squared plus 2, equals 3 times 1, right? I just plugged 1 into these two equations. And we have 3 equals 3, so they do intersect. So in our approximation of what it might look like, probably looks something like this. Yeah? That's not accurate. I'm going to write not accurate, so. But this is our guesstimation. Okay? So when they do intersect, do they have the same slope? That's the real question. If they have different slopes, then it's not differentiable. Alright? So when x is less than 1, f prime of c equals the limit as x approaches 1 of, and I need to write the equation again. You know it. I've written it several times. But I'm just going to plug it back into the equation. The original equation being, I'm just going to do it actually anyway. So, once again, f prime of c equals the limit as x approaches c, f of x minus f of c over x minus c. That's really sloppy, but yeah. So once again, I'm just plugging in. I'm doing the exact same thing. This is only complicated because we have two different equations on either side. So if we're just looking from one over this way, the equation for finding the derivative is going to be different from finding the finding the derivative this way. For the equation for finding the derivative this way. So I'm just plugging in for 1 for c. So limit as x approaches 1, f of x, which we know is x squared plus 2, minus f of c, which is 1 squared plus 2, minus 1 squared plus 2, over x minus 1. And we can simplify this down because we can know what this is. This is just 1 squared, this is 1 plus 2, this is 3. So x squared plus 2 minus 3 over x minus 1. Oh, this is the limit as x approaches 1. See that? See that? It's a little messy. It's squished. I apologize. But when, so okay, so we know from this way over. So what about the other way? So when x is greater than or equal to 1, f prime of c equals something different. This is still the limit as x approaches 1, but now we have a different equation we're working with, so we're going to plug in 3x here for f of x minus 3 times 1 over 1 minus 1. Well, I'm sorry, what? No, x minus 1. I was like, that is not correct. So this is the same, this is pretty straightforward. We can simplify this again. This is 3x minus 3 over x minus 1. Solid? Solid. Okay, so we have our two equations. So we want to know what's happening on either side of these. Is it a sharp turn? Is it a teetering tangent line? So we're going to do the same thing we did earlier. And then we're going to find the slope at 2 points that are close to the point that we want to find, but far enough away so that we don't encounter, discontinuity problems. So let's say at 0.9 and 1.1. Okay. So at 0.9, we will be using this equation, first equation. So f prime of c equals limit of, as x approaches 1, of x squared plus 2 minus 3 over x minus 1. So I just rewrote down the equation that we had up here. I'm going to plug in 0.9. So this is 0.9 squared plus 2 minus 3 over 0.9 minus 1. Still see that? And that equals negative 0.19 over negative 0.1. And that equals 1.9. Okay? Cool. So if we want, oh no, I just ruined my shirt. Oh no. Soldier down. So now we're going to do the f prime of c of this side. We're going to do when n equals 1.1. F prime of c equals the limit. I'm just going to rewrite this down here as x approaches 1 of 3x minus 3 over x minus 1. Okay? So this equals 3 times 1.1. So I'm just plugging things in here. Over 3. Over 1.1 minus 1. Okay? Makes sense? And that equals 0.3 over 0.1. And that equals 3. Now that is a huge difference. That is not, nope. That is a sharp turn. So once again, there's no derivative. This example is important because it's not as sharp as the, as like a 90-degree turn, which is what we're used to seeing. But it's still sharp enough that this isn't going to, that we still can't find a derivative there because it's a sharp turn. Alrighty? Cool. So I just want to quickly go over what we learned today. So we know now that a function is not differentiable. You cannot find the slope at x equals c if there is a sharp turn, discontinuity. We saw this with the asymptote, remember? Or a vertical tangent at x equals c. Okay? Other important point to make. In order, can you still see that? In order for a derivative to exist at x equals c, the graph must have local linearity there. Okay, and this just means, you know, basically what we just went over. In order for a graph to have, in order for there to be a slope that you can find, there must be local linearity. There must be the opportunity for there to be a tangent line. Yeah? And know your formula. And that's it. And with that, I bid y'all adieu. I wanted to say thanks. Thanks so much for having me. I had a great time preparing this and performing this for y'all. Your homework is here, and y'all are in great hands. So, I hope to see y'all soon.